Welcome to everyone to part two of this next workshop. It's great to see so many people here hanging into the very end after lunch on Wednesday. I'm part of a team of presenters that includes Trey Carroll from the NCDOT, who was one of the structural engineers who designed this bridge, and Peter DeStefano, who is the project manager of the contractor Balfour Beatty U.S. Civils, who is actually building this project. And as you will see, just as an effective team is required to successfully complete a flagship project like this, the research that's undertaken as part of this is also part of a team, and I'm pleased to say we have one of our undergraduate research assistants, Sam, from NC State, here in attendance, and one of our PhD students, Paul, who is also here contributing to this effort. My presentation will generally be broken up into four large themes or categories. First is the state of bridges in coastal North Carolina, which is not unique to our state, and it really provides the motivation for why the state is investing a lot of resources into FRP reinforced bridges. Talk a little bit about FRP materials for the benefit of those of you who might not be familiar with the material and are here to learn a little bit more about it. And then I'll get into actually the details of the Harkers Island bridge replacement, followed with just a couple of slides summarizing some of the experiences by the various parties involved in the construction of a bridge like this. This slide here is to give you some context. So we have the state of North Carolina. All the projects I'm going to be talking about is here in Carteret County of North Carolina, just at the southern tip of the Outer Banks. In particular, we're going to be looking at Harkers Island Bridge. I'll talk more about that later. But as part of the motivation, I highlight Ward Creek Bridge and Oyster Creek Bridge as part of US 70 going along the coastline of North Carolina. What really started things for NCDOT was the Harkers Island Bridge. So it's interesting how this has all come full circle. Following an October 2012 bridge inspection, a decision was made that an emergency replacement of that bridge was required. And that bridge was replaced after just 43 years of service. You will see the level of deterioration in these types of bridges. I was told that during the demolition, when they removed the transverse pre-stressing, some of the core slabs failed under their own self-weight because of the level of deterioration, which was the motivation for that replacement. So as part of that, the NCDOT engaged me in a research project that was looking at the condition assessment of two similar bridges in that same coastal area, and then subsequent projects looking at how they can assess the residual capacity of these deteriorated bridges and what can they do to address this problem in the future. The type of bridge in question here is very common in North Carolina, I'm sure in many other states as well, or there might be some variations of this type of precast section. The behavior would all be similar. Hollow core slabs, varying depth depending on span. Very typically, spans are in the 40, 50, maybe 60 foot range, and typically about 3 feet wide. And you normally have about 16 of them side by side. This is a cross-section of the bridge with transverse post-tensioning tying these all together. There's no concrete topping. Typically, there's just a 6-inch maximum thickness asphalt pavement running surface on the top. So this is the type of section that we're talking about. It's been in use since the 60s. We're still building new bridge replacements, new bridges with this type of cross-section. This is the Oyster Creek Bridge, one of those two bridges on US 70 that I had introduced before, 8 45-foot spans. This bridge was replaced after 37 years of service. So we went from 43 to 37. There's a trend here. From this view, doesn't look too bad, right? It's very typical in coastal North Carolina. Bottom of the bridge is oftentimes just a few feet above the water line. At low tide, you can walk out here under the end span, and if you're a little bit taller than me, you can touch the bottom of the bridge. So this just gives you an example of the environment that it's in. From the top, it again doesn't look too bad. You can see these transverse cracks in the pavement corresponding with every bent. These are just simple spans, so the pavement's going to crack above there. And you can see some longitudinal cracks where if you overlay the spacing of those parallel chord slabs, that aligns with the longitudinal joints. And so when you see a lot of these longitudinal cracks, you're probably getting some relative movement vertically due to traffic loading, maybe an indication that you're losing some of that transverse post-tensioning effect. You go to the underside of the bridge, and this is a very strategically located photograph. It too doesn't look too bad. If you look very carefully, you can see a little bit of sort of spalling concrete there. But if you look more broadly, this is what we end up seeing. And this is my colleague, Dr. Mo Purgaz, who was a co-PI with me on that initial project back in 2014, pointing out to us, in case we missed it, the corrosion that's taking place. This was, so here you can see the corrosion. There's a stirrup. These are the corrosion of the longitudinal pre-stressing steel. This was patched. Here you could see a different color patch. So the DOT goes through a process of patching patches. The cycle continues. It starts about 20 years after construction of the bridge and doesn't stop until it reaches a point where a decision has to be made to actually replace it. To give you an indication of what's happening, I hope this video will work. We're on a little barge, and you can see the wave and tides hitting these concrete blocks that are above driven piles at the abutment, and it's just under a continuous saltwater spray. So there's really absolutely no surprise that this is the condition that we're in. Here's another, let me see, how do I get this to work again? Here's another photo of that same bridge during one of the inspections we did. If you look carefully, you can see some blue and yellow hash marking on there. This seems to be in good condition, but by hammer tapping, about a 7 or 8 foot length of this chord slab is totally hollow. There's a significant amount of corrosion that's taken place behind that. You just can't see it yet, and it was only a matter of time before that whole concrete cover was going to spall off. So this was a worry for NCDOT. How were we doing our inspections to really make sure we understand the existing condition of the bridge? What's important here is that after 28 years of service, from bridge inspection reports that we could find going back to 2003, there's already references to patching. And within the following 10 years, once the bridge was finally replaced, half of the end span chord slabs required priority maintenance because they were in the condition of that photo I showed you. And at that time, more than half of the slabs had various degrees of patching that was required because of the spalled concrete due to the corrosion. As part of the research project, we were able to bring 6 of those slabs back to the lab for destructive testing to help the DOT determine what the residual capacity of these deteriorated chord slabs are. The 2 solid blue lines are the 2 slabs we selected that appear to be visibly in very good condition. And you can see here the moment versus mid-span deflection behavior of these pre-stressed concrete chord slabs after 38 years in service. And this black dashed horizontal line is our theoretical calculation according to standards or codes to predict what the capacity of the section is. So you can see, even after 38 years in service, slabs that are in good condition are behaving as we would expect, at least in terms of a capacity perspective. But when we have moderate levels of deterioration, so here what we were referring to was significant amounts of spalling, some rusting being visible. We do the same test and we can see we're getting up to about a 50% reduction in the capacity compared to what would be a good condition beam. And then worst of all, severe deterioration. This is the type of beam that Dr. Purgaz was pointing at, those severe levels of deterioration. you're seeing that the residual capacity is in the order of a third of what the design capacity should be. All right. So, nonetheless, both Oyster Creek and Ward Creek bridges, this is now, I'm showing you a picture of Ward Creek. This is the replacement bridge. Looks very much like the original bridge. And in my closeout presentation to the NCDOT, I told them, I will see you again in 40 years because we have done absolutely nothing to address the problem. This bridge is going to corrode in exactly the same way. We're going to need expensive maintenance, patching, and replacement in a relatively short period of time. Right? So that provided the motivation for NCDOT to look at alternatives. The problem is corrosion. We have a way of addressing the corrosion problem by using this FRP reinforcement, right? So what we did in a companion project, this is the current steel reinforced and pre-stressed cord slab cross-section in the current NCDOT standards. So this is what precasters are used to dealing with. We designed for them a companion FRP reinforced and pre-stressed cord slab, where for the convenience to precasters, we kept exactly the same concrete section, we kept exactly the same strand layout, except for the fact that we're using a different reinforcement material. The precasters' perspective, we were doing the same thing. They didn't have to retool or do anything different. There were some differences because of various knockdown factors and environmental condition factors that are in the code for FRP reinforcement. Here you could see the steel section required only one single layer of pre-stressing on the tension side. If you look carefully, we added two additional carbon fiber strands in the second layer. And then if you also look carefully, the mild steel were number 4 bars for stirrups and for some longitudinal bars up on the top here for temperature shrinkage control. Those were bumped up to number 5 bars when it came to the glass fiber alternative. So a long story short, 2 years worth of research or so, and this is what we get. So all these curves in blue are the ones that we had looked at previously, the residual capacity of those deteriorated core slabs taken from a bridge in service. The line in black here is the moment deflection response of a brand new steel reinforced pre-stressed cord slab according to current NCDOT standards. And you could see, at least in terms of capacity, very similar to what was done in the 1960s. Of course, a brand new section. There's no deterioration of the concrete. There's no cracking or anything. So slightly better response here up to first cracking of the reinforcement. And what's important to observe then, we are very lucky. We actually cast 2 FRP pre-stressed cord slabs. And I say lucky because the first one we tested was FRP1. And you can see it failed at a capacity a bit less than the steel counterpart, prematurely than what we had expected from our calculations and from design. And we said, oh my goodness, what are we missing here, right? We tested the second one, and it performed as we had expected. In fact, a higher capacity than anticipated because really all of those knockdown factors make this a very conservative design. But you can see the response of the red curves for the FRP pre-stressed cord slabs to really match very well that response of a traditional steel pre-stressed section. Now, I'll give you the backstory. Why did this fail prematurely, FRP1? Nothing to do with the pre-stressing, the FRP. Okay, let me make that point. It is an issue of cord sections. During casting, the tie downs for the 2 hollow cores failed near midspan and the core floated. And we actually lost substantial area in the compression zone such that when you take that into account by calculation, you actually predict this capacity very well. So it was a construction issue of cord slabs, nothing to do with the reinforcement. Okay, but we are very lucky. Usually us structural engineers in academia will do one test and say, this is how you design everything. Luckily, we had 2 of these in our back pocket so that we could actually observe what was happening. So, I've talked a lot about FRP. If you were here in the morning, you heard other presentations from 3 other speakers. This is what we were dealing with in this project and also then in Harkers Island. Steel pre-stressing strand, 7-wire strand, we're all used to seeing that. The alternative is a carbon FRP strand. This particular product produced and looks the same in terms of its geometry as the steel counterpart, but this is entirely carbon FRP. There is a PET wrap that's wrapped around each of those 7 wires for protection of the carbon fiber and to enhance the bond of the strand to the concrete. And then it's very common to replace mild steel with glass fiber bars. So I show a glass fiber bar here. The image on the right is to show that to enhance and develop bond between the glass fiber bar and the concrete, various surface treatments are possible. It depends on the manufacturer as to the type of surface treatment that's used in order to develop the bond. So these are only, I'm only showing here samples of FRP products that are used for reinforcement in new construction. There's a whole other suite of FRP products for strengthening and repair applications. That's not the topic of the presentation today. FRP is a composite material, just like concrete is a composite, just like steel is a composite. It is made up of fibers. The fibers are what produce or provide the strength and stiffness of the cross-section. There are various types of commercially available fibers out there. And those fibers themselves have the structural integrity to end up being a bar that we can use through a matrix. The purpose of the matrix is to protect and transfer load between these fibers. If you can imagine, we're applying stress to fibers around the perimeter. They need to transfer that stress to those fibers within the cross-section. That's being done through a shear transfer mechanism in that matrix. It's a polymer resin. We used to call these plastic bars, right? But now we're calling them FRP polymers. And there's various types of resins that are used depending on the application. So together, the combination of this is what we're referring to as the composite or the FRP. What you'll notice is very uniform diameter fibers, very, very small. You probably can't read this, but this scale here is 10 microns, nicely uniformly distributed through the cross sections. Very, very large, long aspect ratio. These are continuous fibers along the full length of the bar. If we look at tensile behavior, and this is a plot of stress versus strain, here in black you can see a typical stress-strain relationship for your standard grade 60 steel. Of course, idealized, we're not showing a strain hardening response post-yielding. And then for reference, typical stress-strain relationships for various types of fibers, and even for a particular fiber, depending on the manufacturer, depending on the product, the stiffness, this rupture strength can vary within some reasonable range. Glass fiber, again, is to replace the mild steel. You'll see it has a stiffness that is less than that of steel. In fact, the stiffness of glass fiber, as sort of a rule of thumb, is closer to that of concrete than what it is to steel, but a rupture capacity that is several times higher than that of a grade 60 steel. And although these are, of course, lines that were drawn as linear in Excel, we have experimental data. This is very realistic of the response. These are elastic materials that fail by rupture at a particular strain with no yielding or plateau. Then we have the carbon fiber bars or systems, much higher stiffness. We're getting closer to that of steel. And then as you go to a stronger material, it becomes more brittle. So the rupture strain for these higher strength, stiffer carbon systems is less than that of the glass fiber. Why are we using these, though? I hope I made the point in my first few slides. We remove the iron from the reinforcement. We totally address the corrosion problem. And if that's the primary reason for the deterioration of the infrastructure, for the location of that infrastructure, then this is an effective way of addressing that. High strength to weight and stiffness to weight ratio. We're looking at materials that are in the order of 25–30% that of the weight of a steel counterpart. Other advantages, because there's no iron, it's electromagnetically inert, and in some applications that is an advantage. We heard this morning someone talking about the use of glass fiber reinforced rooms in reinforced concrete buildings, hospitals that house MRI facilities where the steel reinforcement might interfere with the magnetic resonance. Ease and speed of installation. You cannot underestimate the impact of the light weight and that it has on the ability to handle the material on the construction site. More material on a truck, less transportation costs, lighter cranes on site, or maybe even eliminating the need for some cranes to handle materials on site. Not so much in the reinforcing bar products that we're talking about, but because the mechanical properties are related to the fibers, you do have the ability in some applications to define a fiber architecture to suit very specifically the projects or the intended needs. And another factor is low thermal conductivity. We're starting to see the use of FRP reinforcements in the precast industry, particular insulated wall panels, where the steel truss is being replaced with fiber systems to provide that structural composite action without creating a thermal bridge through that insulating core. Right, these are all the good things. It would be remiss of me to not talk about some durability-related issues of composites. No matter what material you use, right, there's going to be good and bad with it. You might say that the linear elastic behavior of the material is a disadvantage, but I would argue that our design codes and guidelines have developed to allow for that appropriately, such that designs remain safe, although we have to think about things in a slightly different way than we're used to dealing with reinforced concrete. We talked about in the morning its susceptibility to high temperature and fire. There are very reasonable and sensible guides and information out there that talk about how you can achieve fire resistance of structural members. In my particular application today on bridges, this is less of a concern. We don't often think about fire rating for bridges in an outdoor area. And being a polymer or a plastic, it's sensitive to UV radiation. But because we're talking about internal reinforcement, except during the construction process, it's then entirely encased in concrete, and of course that issue goes away. Even so, I have heard myths from precasters and contractors. The material arrives to site, we got to cover it up. It can't be exposed to UV. That is not the case. It can be out there for weeks or months without protection. It's going to be perfectly fine. So we got to be reasonable about it and not panic by what you might hear out there. And I'll point out a few other places where that's true. So there's various types of products that are available that are used in the construction industry. First of all, we get these fibers, glass or carbon, or it could be basalt, in these rovings. Think of this like very long spools of thread. And then you can weave through very much textile type technology. You can weave fabrics or sheets in various architectures, and these are mainly going to be used for strengthening applications. You can create shapes, pultruded shapes, just like we have steel sections. And then, of course, you can produce various bars. So I thought it would be good to provide you with some samples. By a show of hands, who has never held or seen an FRP bar? Two courageous people, okay. There might be more in the room, too. I've got a sample of a steel strand, 7-wire strand, and the 7-wire carbon fiber strand. These are the actual products that are being used in the Harkers Island Bridge and in other similar bridges. And then I have 3 samples here of glass fiber bars with different surface treatments, so you can get a sense for how different manufacturers are handling the bond issue. You can see different colors of bars. Usually we think of glass FRP as that white or yellow color, but depending on the resin they're using, we're seeing now very different colors, and so you'll see a black bar here, but in fact that's actually a glass fiber bar, not a carbon bar. And then finally, you're going to see in the project, the project uses a square spiral for transverse reinforcement in piles. Here's a sample that was cut. This is actually a 16-inch square spiral, but you can see the bend that was introduced into that cross-section, and we're going to talk more about that as well. Just to share a little bit about the manufacturing process, this is the pultrusion process for reinforcing bars in the form of a schematic. Various manufacturers have their own proprietary ways of doing it, but in terms of the concept, this is generally what it is. You've got a number of racks here with those fiber spools that go through various guides that brings these bundle of fibers down into that circular cross-section that we're looking for. It goes through a heater, and then the dry fibers are impregnated with the resin that is compatible with that system. It goes through heaters. The heating of this bar accelerates the curing, and it's a pultrusion process, so there are then these various guides here with, in this case, hydraulic actuators that are pulling this bar through to get the final cross-section, which then, of course, cut to whatever length is required. There was some discussion in the morning sessions about bending, right? Once the resin is cured, you've got your perfectly elastic material. You can bend it until you would reach the rupture strain, but if you bend it prior to that and you let it go, it's an elastic band. It's going to go back to its original shape. So bends have to be introduced during the manufacturing process before that resin is fully cured. And that requires understanding and communication. I'm going to talk about that later on. In the production facility, we've got bundles of glass fiber bars stored just as you would in a steel mill with steel bars. And yes, you can bend them. You can bend bars, but again, a bit more planning and communication is required to get this done effectively and efficiently. In terms of carbon pre-stressing, you require special connections in order to stress the carbon fiber. And the reason is because all those wonderful properties I talked to you about are in the direction of the fibers. So it's all longitudinal. Very high tensile strength and stiffness. Transversely, now to stress it, I need to grip that bar transversely, give a confining pressure to pull on it. Without some treatment, I would locally crush the fibers there, the cross-section. I wouldn't be able to stress it to the level I need. So here a coupler system was developed by the manufacturer. You first wrap the 7-wire carbon strand with a soft buffer material to reduce and distribute those confining stresses, that pressure. You then have a wedge anchor system that gets wedged into a threaded coupler. And the reason why that coupler is threaded is because that is then connected to a traditional steel chuck to the steel strand on the other side of this. And this next schematic is going to illustrate that. This is an example of pre-tensioning in a precast plant. You've got your form, you've got your carbon fiber cable extending beyond the boundaries of the form for your element. You then have a coupler on either side that transitions from the carbon strand to the steel strand. You got your dead end over here and your live end over here. This is a blow-up of what that looks like. The coupler on the carbon fiber strand here is on the left side. You've got the shorter steel coupler on the right side. That's looking at this application over here. And then a threaded coupler that connects the two together. Okay? So FRP reinforced and pre-stressed concrete is, I think we all have to agree, still a new technology. That's why we're having these kinds of workshops. But I would argue is no longer an emerging technology. Why do I say that? We have bridges and services in Japan, Canada, the US that have been out there for quite a time. There have been studies by University of Miami in collaboration with Missouri S&T, and I think there's another one or two universities that pulled glass fiber bars from bridge decks and tested them. No signs of deterioration yet. Right? So the performance in existing bridges has been out there for a while now. No indications of anything going wrong. In the US, this number here I got from a particular manufacturer 2 or so years ago. I think it's probably bigger than that now. It's being used in a number of states. You'll notice the states shown here are those that use probably a lot of de-icing salts or in coastal areas. North Carolina is missing from there. About 2 years ago, there were 6 new bridges or demonstration projects under design or construction. I know that number is more because of what's happening in North Carolina alone. But beyond field applications, through AASHTO, we have various design guides and specifications that cover the use of glass and carbon reinforcement. ASTM D30.10, which is the subcommittee on composites for civil structures, is developing and already has a laundry list of standardized testings to qualify the materials we're using in bridges and other civil infrastructure. And here in ACI 440, you've all heard and know that the 440.11 building code requirements using for the first time glass fiber reinforcement has been approved and in fact has just been adopted by IBC. So what led up to the decision for NCDOT to use this for the Harkers Island bridge replacement? They didn't have a long history, and in fact NCDOT was historically very, very conservative. Their very first application of FRP was in a bridge deck in 2005. This is a bridge deck on top of AASHTO Type 3 girders up in the mountains of western North Carolina. After that, they engaged NC State University through me on that cord slab project I had talked to you about leading up to the motivation for this bridge. This is an example of that carbon pre-stressed cord slab. You can see that second layer of pre-stressing there. Prior to failure, you can see the significant amount of deformation taking place, just as we would have achieved with the steel pre-stressed counterpart. So that was in 2014. That was a year after the emergency replacement of the Harkers Island bridge because of the deterioration. This project completed in 2016. And subsequently, NCDOT has been a member or a part of various other TRB pool-funded projects. So not a lot of history, but enough for them to be confident to design this bridge. So Harkers Island, a significant bridge. I call it a flagship bridge for North Carolina. You'll see why in a second. Servicing a population of only about 1,100 permanent residents in Harkers Island and actually declining, and an area of less than 2.5 square miles. The only link to the mainland is to the top of this photographic image here, is by the existing bridge. There's actually 2 bridges. There's a small island here where the 2 bridges span over. Here's a photo of the one bridge. This is the superstructure that was replaced in 2013. And then the second span, the second bridge, has a mechanical swing span and is classified as structurally deficient and is currently load posted. So these are the 2 bridges that are being replaced by the single Harkers Island bridge replacement. These mechanical Swing spans or really any kind of a navigation span like this, I think most DOTs are doing what they can to get rid of them. They're a maintenance nightmare, particularly in an area like this. The condition of the existing Harkers Island Bridge, right? Same photos over and over again. This is happening on every single bridge along the coastline. And here you can see additional deterioration at one of the pile caps here. Some wrapping of the piles for the bridge there, which we didn't look at for the Oyster Creek or Ward Creek bridges. But again, exactly the same thing, patches on top of patches, spalling, corrosion taking place. The NCDOT engaged the local community significantly in the design of this bridge replacement. You can see here this was one of many alternatives that were presented. Here's the existing bridge alignment. In red, you see the new bridge alignment. The navigational swing span is replaced by a high-rise bridge portion with a navigation span over there. What resources were available and leveraged by NCDOT? At that time, ACI 440.11 didn't exist. So they referred to the .1R design guide that was the predecessor to .11. They referred to the research report we provided to them through that cord slab research project and the AASHTO documents. They referred to their counterparts at Michigan, Florida, and Virginia. The one thing I'll point out, and I'll share with you how this becomes significant, the scale of Harker Island Bridge compared to the bridges that these other states have designed is at a whole other level. And it brought to light some additional things that were not perhaps realized before. So some project details. It's a 3,200-foot long bridge with 28 spans. It's about 0.6 of a mile, 1 kilometer long. About 1 million feet of carbon fiber pre-stressing in both the driven piles and the girders. About 1 million feet as well of glass fiber reinforcement in the substructure and the superstructure primarily being the bridge deck. The only element of this bridge that does not include FRP reinforcement are the barriers. The barriers that they're using on this bridge have not been crash tested with FRP bars, and so they've got epoxy-coated bars. I'm going to be excited to go to that bridge in 20 or 30 years' time and to see those barriers corroding while the rest of the bridge isn't still in good condition. It's about a $60 million bridge. Remember servicing 1,100 people in Harkers Island currently. And there's a moratorium during the summer months because this is an environmentally sensitive area. There's oyster harvesting, a very big tourism area with fishing, and so no work within the water is allowed during those summer months. This is a photograph of progress that would have taken place just prior to April 1st last year. The contractor strategy, so on the bottom of the picture here is the mainland. The contractor strategy was to get as far as they can get with all the pile driving, all the work in the water, so that when the moratorium's up April 1st, they're working on the superstructure. So a lot of good strategy. What you're seeing along the left side here is a temporary trestle bridge. This is a very shallow site. The water draft in some areas are less than 3 feet. And so you couldn't use barges effectively for most of this bridge. Here you can see a public boat launch. To the left here and right on the bottom is actually the field office site. Balfour Beatty was lucky to be able to negotiate a lease arrangement with residents to lease that land. They were good citizens of the community as part of this project. They've built temporary fences. They're maintaining a driveway through their field office and staging site here for residents to get to their homes, which are just to the left in the image that's shown here. At the completion of the bridge replacement, this bridge will be demolished and removed. This bridge will be retrofitted mainly by changing the barriers so that it will become a pedestrian bridge allowing pedestrians to get to this island and a fishing pier that's currently on that island. NCDOT is expecting at least a 100-year design life with no major repairs or maintenance required. Right? Remember, they're replacing a bridge that, where the superstructure of this bridge was replaced after 40 years of service. Right? I don't expect you to see this, but how did NCDOT go about the process of letting this project? I took a snapshot of just a few pages of the special provisions for the FRP materials. It talks about qualification of the materials, geometric properties, and then long tables with a laundry list of various ASTMs that are required to qualify the materials, the FRP materials being used in the project. At the front end of this, NCDOT is part of a growing consortium of state DOTs that are engaging the FRP Institute to produce the third-party independent certification of the plants. And there's a growing number of FRP production plants that are certified by the FRP Institute. This gives the DOTs the confidence in the quality and the QA/QC measures of the plant to provide the materials used in their bridges. Right? The trouble comes at the back end because the current special provisions, which NCDOT took from Florida for one of Florida's recent bridges, requires this long, and this is not the full table, by the way, requires that same long laundry list of ASTM material testing for the materials that are then delivered to the site or to the precast plant. When you're designing a 1 or 2 span bridge, that is manageable. A 3,200-foot long bridge using 100 lots of material, requiring whatever this is, 12 or 15 ASTM tests with 5 replicates. This is a massive undertaking, a massive undertaking. You'll see with some of the next slides, state DOTs do not have the equipment to do these qualification testings. They don't have the time and people to undertake these tests that are currently required. So to me, this is a work in progress. I'm working with other state DOTs as well. What can we do if we have a pre-approved material that is in the state DOT's approved concrete reinforcement suppliers list because of this certification? We don't need to repeat all these tests for the material delivered to site. We don't do that with steel, right? In steel, you're going to take a few random samples, do a tension test most likely, and you're going to be satisfied, right? So this is where we need to work to make things more efficient. Just to give you a snapshot of a couple of the tests, this is the ASTM for tension testing. So you're going to need a steel sleeve to grip the FRP material, and you're going to need some kind of grout or filler material between the steel sleeve and the FRP bar. Right? We require this steel sleeve to grip the bars in order to tension them, right? We talked about that from the pre-stressing before. So this is the ASTM schematic. This is what Paul and Sam devised in our lab. So we can prepare a number of these at a time. The process to get to this stage is in the order of a week. You have to first cast the steel tubes on one end here with the grout, let that grout cure at least a day or so. You then flip them over, and then you do the same to the other side. Right? You got to let that grout cure in order for it to have enough strength to transfer the stresses from that steel pipe to the carbon fiber. So unlike a steel bar where you're going to get your sample from the field, you're going to stick it in a universal testing machine, you're going to pull it, you're going to look at where your yield is, and you're done in a few minutes. This is not a difficult test, but from the time of preparing the specimen to be able to test it, you're talking about a week lag. And then we do the test. This is our MTS machine at NC State. You'll see we have the carbon fiber bar encased within a clear PVC tube with a little cutout here allowing us to install a displacement transducer to measure displacement so we can get strain. So from this test we also get modulus. This is what the failed specimen looks like. There's no more material in the middle there because it's an explosive, elastic, brittle failure. And if I can get this video to work, you will see an example of a test. And so that's it. Slow motion for dramatic effect. You see we have removed the transducer from here because at that failure, if we leave it on, we're going to be damaging our instrumentation. And we don't need strain all the way up to failure to get the modulus because it's an elastic material. Another important test is bent bar. I'm just going to talk a little bit about this. You saw that sample of that solid circular carbon fiber bar that is part of this 16-inch square spiral. That's the transverse reinforcement for the driven piles. When you bend FRP, because the fibers are no longer straight, you get a reduction in capacity. And so for designing a bent bar, we need to know what that rupture capacity is, the bent bar. We do that with this bent bar test. We take one of the loops of that spiral, put it in the form here, we cast concrete on the two sides. We break the bond between the straight leg of the bar and the concrete on one side, and we push those two concrete blocks apart with hydraulic jacks. So we're putting tension into those bars. We're going to measure at what stress are those bars rupturing when we put a bend in there and compare that to the straight axial tension test. This is what failure looks like. One of those two sides are going to fail because it's going to reach its capacity first locally there. The failure is always right at the start of the bend, and here you can see an example of the rupture of that bar. So let's get to the bridge here. Some details. You're looking here at the navigation channel of the high-rise portion of the bridge. This also is the longest span of 160 feet. I'm going from memory. I think we're providing 45 feet of vertical clearance at mean high water level based on a study that was done by the DOT looking at the ships going across this strait. The navigation span is the only one that has the bents on a skew. All the other bents don't have any skew with the longitudinal axis of the bridge. There are two types of substructures. Prior to the high-rise portion of the bridge, you have either 5 or 6 24-inch square driven piles with a cast-in-place pile cap. When the girders are placed directly on top, there are 4 girders on each of these pile caps. The second form of substructure has now 2 rows of 5 driven piles, so there's going to be 10 piles in these with a cast-in-place footing, 3 4-foot diameter circular columns with a column cap cast in place on top. All of this reinforcement detailing you're seeing here is all FRP reinforcement.
Question.
Yes?
With these FRP bars, do you use tie wire to tie them together?
The question is about tying the bars. I'll show you that.
Okay.
Yep. Looking a little bit more at the square piles, 24-inch square pile, 16 strands around there, the carbon fiber spiral, as you can see here in this elevation with varying pitch along the length of the pile. The longest of these piles were in excess of 100 feet, usually those ones that were the test piles to get the depth that are going to be required for the remaining piles. Coastal Precast Systems has the contract for producing these piles. This is at their Chesapeake plant. You can see their existing forms being used for the carbon fiber pre-stressing and the carbon fiber spiral, casting concrete as you normally would, delivered by truck one at a time. Each one of these truck deliveries is a permit load coming down from Chesapeake to Harkers Island down to the site here. Pile driving using an ICE, International Construction Equipment, 62 hammer. Pile driving, doesn't matter, this is FRP Prestressed. They are driving in the piles in exactly the same way as they would steel piles. You can see the driven piles for the various bents in this photo here. Of course, each pile gets driven a different amount according to that design resistance. They are then cut off to the correct elevation and embedded in that pile cap. This is something that has been observed and is common, which is different than steel. The bond between the carbon fiber strand and the concrete is very good. It develops over a shorter length than it does for steel strand. And what we're observing is longitudinal splitting that's taking place. That's, of course, aligned with the location of the strand. And in cross-section, this was one of the cut portions of the pile. They saw cut around the perimeter just beyond those strands, and then just tip that over, and that core is going to snap off, right? So, again, typical procedures that you would use. But what you'll see, depending on the age of the pile, are these splitting cracks. And you can see here 20 inches. They usually range between 18 to 24 inches, which is related to that development length, transfer length of those strands. The bond is so good, it's creating higher radial stresses that's causing that longitudinal splitting to occur. This happens in the precast plant, and it happens to piles that are cut in the field that are still relatively young. The concrete strength at de-stressing in the plant is a little bit higher than 6 KSI. These have 10 KSI design strengths. Piles that are driven in the field and left there for several months before they're cut do not exhibit this cracking. And because the concrete strength has achieved enough tensile capacity that it prevents this from happening. But the bottom line is, expect to see this happening. The cracking is less critical because we're dealing with a non-ferrous material, so corrosion is going to be a problem. And for the piles, these piles are embedded 2 feet into the footing, so that crack is fully within then the cast-in-place concrete, so it's also protected. Here's this is at the construction site, the staging area. They're building the reinforcement cages. This is for those 4-foot diameter columns. Glass fiber bars longitudinally and the spiral, despite the black color, that is also glass fiber spiral. Here you can see the reinforcement cage for one of the cast-in-place pile caps with those driven piles embedded 2 feet into it. Something else to watch out for. Here's the design intent from NCDOT, and this shows that, that lagging understanding or maturity from the NCDOT structural engineers to practice. If this were steel, they define this bar, it's labeled as B2, as one single bar. This is about 30 feet long with a bend and a hook on each side. This was what was in the construction drawings. That's the bar schedule there. The problem is, you go to the FRP manufacturer and they say, we can't produce that. Manufacturers have these bent bar detailing tables. And again, I know you can't see this, but this shows the standard bends of GFRP bars. If we look at this one here, it tells us that if this short length A is less than 24 inches, which was the case for that particular bar detail, the maximum length of this straight leg here is 110 inches, nowhere near the 30 feet that we were asked for. So this is just an example of where you need to understand how these bars are manufactured. They're not bent in a steel fabrication plant. You cannot have a 30-foot length of bar while it's being protruded and bend it to produce that bend as it's being manufactured. So the solution is simple, right, in that you have your bent bar, and then you just splice it with your longitudinal bar. So the end result is the same. You would avoid a lot of headache if you're just knowledgeable of that up front. The structural engineers would know that. Detail it appropriately, and then you have a perfectly reasonable solution in the field. Here's just some construction in progress. pile cap. Here you can see the varying heights of the 3 columns for the high-rise portion of the bridge. Here's the cross-section of a typical superstructure, 4 girders, cast-in-place deck on top. This is just a 2-lane road. It uses floor to I-beam cross-sections of 54, 72, and 78 inches. The 54s span 100 feet, the 72s 130 feet, and the 78s I think are only used on the navigation span, which is a 160-foot length span. All of the transverse reinforcement is glass fiber. All the pre-stressing is carbon fiber strand. Coastal Precast is doing this project, the girders as well. This is either in their Wilmington plant in North Carolina or up in Virginia at another plant they have there. You see the large spools of the carbon fiber strand being delivered. Yeah, it's exposed to a bit of sun. There is a roof over the top to provide some protection. Here you can see the pulling of the longitudinal strand, the couplers that we had talked about previously. They're staggered because the couplers, of course, have a bigger diameter, so you can't locate them all in the same place. Here you can see some of the carbon fiber strand going left-right with some of the tying of the transverse reinforcement. The question about ties, there are a number of alternatives. You can have zip ties, plastic zip ties. What they're using on this project are epoxy-coated steel ties for the ties. Some more construction in progress. One of the unfortunate things, we tried so hard to make this totally steel-free, except that lifting was an issue, and so we went with a stainless steel lifting hook mechanism. In fact, Balfour Beatty doesn't like this. I'm going to work with the DOT to develop a design detail for an opening through the web so that we could put in lifting pins to move it, but that kind of a detail doesn't exist, and that's why it wasn't used. But I think, an opportunity through our research project to make these more effective, more efficient in the future. Construction after that on site remains the same. The girders in place, the formwork for the cast-in-place deck. These are glass fiber bars providing some shear connection to the cast-in-place deck, and a glass FRP producer's dream. They said up to 1 million feet of glass fiber bars used in that deck. No special handling, being used here on site. Some construction in progress. You can see the various stages of construction of those bents leading up to the high-rise navigation span there. Here, some of the girders being in place, casting the concrete behind it. Balfour Beatty are ahead of schedule on this project. No delays related to the use of FRP material, even though this was their very first project using FRP. Here you can see installation of the girders for the navigation span. I love seeing this. They've got some great photos of these girders on barges. Coastal Precast in Virginia is located right on the Intercoastal Waterway. They stack a bunch of these on a barge and ship them down by barge through the Intercoastal Waterway from Chesapeake down to Harkers Island. The crane's putting the first of the 5 long span girders in place there. So, what have we learned with all this for now? Really, the same applies to any project. Effective communication is key. The structural designers should be aware of limitations of using bent glass fiber bars and to plan and schedule and have good coordination with the FRP bar supplier to avoid any unforeseen delays in the future. Be aware of the lead time associated with production and refabrication, right? If something isn't right, you can't just call them up and say, I need a bunch of these bent bars delivered next week. There's a lead time for that to happen, right? Repetitive bar shapes help. You can have perhaps a stockpile of these bent bars. Should there be an issue, you've got another supply on hand to cover you until you can get a delivery of a new set. Good specifications. Balfour Beatty talked about the good specifications provided by NCDOT, particularly in terms of handling and storage. And I think a myth, you don't need to treat glass fiber bars with gloves, so to speak. You can walk on them. They can take a bit of beating. They're not going to break on you. So keep that in mind. Be aware of the potential for a local splitting when detensioning with the carbon systems. Effective detailing and maybe a bit of more attention to concrete strength at detensioning will likely help you with that. And this is sort of a research project related point here to address that lifting hook problem and totally getting rid of all the ferrous materials, coming up with ways in which we can do that without the lifting hooks. And critically evaluate the testing requirements that are required for the materials delivered to site. I talked about this before. Most DOTs are not going to be able to do that. You know, Florida in their specifications says that testing needs to be done at Miami or Sherbrooke or, you know, the very specific facilities. NCDOT is doing that with us. But let's find ways to make this more efficient, given that we're getting materials that are being delivered from independent third-party certifications. And so the $60 million question for this bridge is, okay, we're nearly finished this bridge, would you do it again? And the answer from all three relevant parties was an absolute yes. And to me, this is the most powerful thing, right? Because if you had a bad experience, you're going to say, okay, we tested this out, guys, but we're not going to do this anymore. Coastal Precast, the precaster. By the way, I believe likely the only precaster in our region that bids for these projects. But they're happy to bid for them. They've got 3 crews that are trained and dedicated to using carbon fiber prestressing. Right? They're not starting up with a new crew that have to be trained with the procedures every time they get a job. They're simultaneously producing members for the Hampton Roads Bridge Tunnel project, which is also using carbon pre-stressed piles. So they're getting a lot of work. There's a trade-off. They will use their casting bed for 3 casts per week when they're using steel pre-stressing. Because of the extra time for that coupler system, it goes down to 2 per week when they're using a carbon fiber system. But they're set up with their schedule and their crew to accommodate that. This is part of their operating procedures. From Balfour Beatty's perspective, this was their first ever FRP project. Yes, they will bid on other FRP bridge projects. They commented on the lightweight, ease of handling, reduced trucking costs. And Peter, from his perspective, says they treat the material the same on the site, whether it's glass or steel. So they're not making really any accommodations because of that. And NCDOT, they're recognizing the benefit of FRP technologies to make the bridges more durable, right? They're owners that have a long-term investment in there, right? There's a real cost to them if they got to replace that bridge in 40 years, which is not hypothetical. They're doing that on every bridge along the coast right now. And currently, I think this is the icing on the cake. At least I personally am aware of 3 other bridges that they're planning to let that's going to be spec'd with FRP reinforcement and pre-stressing. So they're moving ahead with it based on their experience. These are the collaborators. I purposely put NCDOT in the middle here because if it was not for their interest in adopting this technology, none of this would be possible. Tokyo Rope is providing the carbon fiber strand. Owens Corning and their plant out of Concord, North Carolina is producing the glass fiber bars, and Coastal Precast doing all the precast. And I just love this image. Peter loves flying drones. He's the project manager for Balfour Beatty, and this is a great picture that is almost up to date. It's probably a month or 2 out of date here, but the current state of construction. So thank you.
What were the cost or the cost comparison between traditionally reinforced bridge and this FRP bridge?
So I'm not the best person to answer that question. because I'm not involved in that side of it. Yes, this bridge at a first cost is more expensive. I mean, absolutely. The glass fiber bars, at least with current market conditions, should be pretty well 1-to-1, especially if you're using straight bars. When you have a lot of bent bars, that starts to add cost. Carbon fiber certainly will be many times more than their steel strand counterpart, but you're using a small percentage of this material in the overall structural elements, and that material, as part of the whole project, is a relatively small percentage. And to me, the biggest thing is, if we replace this with the same steel bridge, steel reinforced bridge, we will be replacing it again in 40 years. And you got to factor in that cost. In addition, the maintenance, the patching, which is documented, all of those costs, there's really no comparison to make. I didn't show cost as a negative because I think it's a moot point when you look at life cycle assessment.
A couple of more. The piles, they were wrapped in CFRP stirrups, and you tested those. Two questions regarding that. What was the knockdown in tensile strength, and why were CFRP stirrups used as opposed to GFRP?
A good question. So there actually isn't a bent bar ASTM for carbon fiber. So we're kind of doing this as part of the research project. Preliminary data is telling us that we're losing about 50% of the straight bar tensile capacity because of the bend. For glass fiber bars, this is, I think, 60-something%. So this is known, and it's included in the design guides. But you need to know what that value is so that you can design it appropriately. The NCDOT allowed for glass or carbon reinforcement for that spiral. They chose to go with carbon because there were previous piles that were done in that way, so there was an element of comfort with it. That circular carbon bar is of a material that is a bit cheaper than the strand, so it's a little bit more cost effective, but certainly there's a premium. Furthermore, there's a debate that's going on. What is that transverse reinforcement actually doing in a driven pile? Should we be matching strength from the steel counterpart, or should we be matching stiffness? And that will also might drive you one way or the other.
Okay, and from a material standpoint, I know the code addresses creep rupture, and I think you listed one of the negatives, but how are GFRP bars, how is creep relaxation addressed? Not creep rupture, but creep in itself, because a polymer in itself will creep, and unless the load's removed, it can come back, the cross-linking would have, but or the polymer chain, but how is it addressed in terms of creep relaxation, not creep rupture?
So for the glass fiber bars, I don't think the creep relaxation is an issue for glass fiber bars that's being used as mild reinforcement. The creep rupture limit for the glass fiber bars is related to the self-weight, and there's a limit to that stress. For the carbon strands, there were tests done. Lawrence Tech, Dr. Nabil Grace has done some of this for the product that was used here to look at that relaxation and long-term losses. Historically, the jacking stress for these kinds of strands were 65% of guaranteed tensile, and that's actually being bumped up to 70 or even more. The other thing to keep in mind is the actual rupture stress for these strands are actually much higher than their guaranteed tensile strength, and so we're really at quite a low stress, relatively speaking.
Right, but are you saying that creep is not a phenomenon at low level loading that with GFRP bars that you need to be concerned about?
I'm not aware of that being an issue.
Okay. And a comment, you talked about the barriers. There is an NCHRP project, 10, I think it's 110 or 117 to look at and crash test barrier rails with GFRP bars and to
Yeah.
repair those.
Yeah, I'm aware of that. Yeah, I know some of my colleagues who bid on that. Yep. Thank you.
Thank you for excellent presentation. I just have a question regarding post-tensioning. Can be these FRP tendons used for post-tensioning because of the pre-tensioning process is a bit complicated?
Yes, the short answer is yes. It has been used for post-tensioning. This morning there was a presentation regarding Michigan DOT where they used it to post-tension box girders. The system is more user-friendly for post-tensioning. The material gets delivered with a proprietary system, a stainless steel coupler at the end that is conducive to the post-tensioning. So yes, it can. It's actually more user-friendly to use in a post-tensioning application in terms of the time and effort.
Thank you. And regarding the long-term behavior of material properties, let's say about the long-term strength and maybe the fatigue, is there any degradation during the lifetime of the tendon or not?
Fatigue is really not an issue. The carbon fiber systems are very robust in terms of fatigue, so fatigue is not any worse or more of a concern than a steel strand. And you know, accelerated testing, durability testing is being done in labs. You know, the proof will be in the pudding, right? Once these bridges reach, hopefully, their 100-year design life. But you know, that very first bridge that I showed in Japan that was carbon fiber prestressed replaced a bridge that was demolished within, I don't remember exactly, roughly saying within first 10 years of service because it was corroded so badly. That bridge has been in service now for, I think, approaching 30 years or so. There's been no signs of any degradation whatsoever. So yeah, I think there's enough evidence coming from the field that durability is going to be what we expect it to be. The materials, the systems are performing very, very well.
Thank you.
Can I have one question? Very simple one. I want to asking about the connection between the girder and the deck. There is the GFRP bar is using that like a dowel. So is there any consideration on the dowel for each end or more severe for the shear friction or shear force transfer from the girder to bridge deck?
Yes, you're correct. So there's the shear connection of the cast-in-place deck is enhanced with
Yes.
the glass fiber dowels that are coming up from the vertical legs of the
Yes,
stirrups.
glass fiber is very weak in this kind of the
Yeah,
dowel.
but if you notice, it's a relatively close spacing, and there's also a very wide top flange of this Florida I-beam where you're going to get some additional
So
shear
you
transfer
Consider
mechanism from
about
that.
not only the glass fiber dowel, but also the friction between concrete and concrete? Yes.
Yeah.
Thank you.
Thank you.
Thank you very much.